Okay, so thank you everyone for attending. Today, Inneke is going to be talking with us about the perceiver. The perceiver is a new iteration of the transformer architecture. The authors claim that it can generalize to a whole set of new tasks, which is quite a bold claim for a single architecture. And it's a very recent paper, so it should be in the spotlight in the near future. Let's see it.
Hello, everyone. Yeah, thank you, Carlos. So, okay, I'm going to share my screen. Okay, can everyone see my screen?
Mm-hmm.
Yes.
Yep.
Yes.
Okay, good. Yeah, I just let it organizing my window. Okay, so yep. Hello again, everyone. And as Carlos has mentioned before, today we're going to talk about a paper called Perceiver. It's a paper from Google DeepMind, and it's really new. So yeah, this should be a new interesting architecture related to transformers. Okay, yeah. So what is this paper about? The problems that this paper is trying to solve is that first, in a lot of deep learning architecture, we have a lot of them has inductive biases. For example, convolutional neural networks that, for example, in a picture that maybe I can draw some, like if we have a picture, the pixel is like there's inductive biases that we assume each pixel is having like some sort of relations with the surrounding pixels. That's how CNN works, because we're doing some like moving windows and we assume that those pixels have relations to each other. So that is one thing that we call inductive biases in deep learning, that it's very common. This is good because these biases will help the model to learn, but it's also kind of a restriction to the model that it can only be used to a specific task. This paper introduced a new model called Perceiver that use a transformer. It's built based on transformers, which is architecture that actually doesn't have these biases. That's why they mention transformer has a few architectural assumptions. But transformers is actually having another problem on its own. That is, if we scale the inputs, we're going to have a quadratic memory and time complexity. So this paper is saying that a transformer is good, that it doesn't have these inductive biases, unlike CNN, but it also has another drawbacks, that it has the problem of quadratic complexity. So this paper wants to make use of this, the fact that transformer doesn't have inductive biases, but we want to get rid of that quadratic complexity. Okay. Yeah, basically that's the basic idea that they explain in the introduction. So, okay, I think to make it clear, we can just go to the methods directly, because basically the introduction is like that. Okay, first, maybe I'm going to talk a bit about what is the quadratic problem in transformer. Maybe if any of us is not really aware of it, although I think we already mentioned in some paper club before. It's like, for example, we have Just imagine in NLP where we have a sentence of like 10 words and we pass this sentence to the transformer. The self-attention inside the transformer is going to, like, for each word is going to attend to every other word. So imagine when we scale up the input from 10 words to like 1,000, then the complexity is become like, it becomes a squared operation. So it's quadratic operation. And that becomes a huge problem if we want to use a transformer in vision. There is a
Excuse me, could you perhaps repeat again what the transformer is actually doing? My memory is not as good as it used to be.
Okay, so yeah, like for example, we have 3 words in a sentence. This is our input sentence that is going to be passed to the transformer. Inside the transformer, there are self-attention blocks. That actually what's the attention blocks doing is that for each word, for example, this is the first word, second word, third word, we're going to attend to itself. Sorry for my horrible drawing. And then the second word is going to also attend to that words, and this is the first operation, and then we need to do that again for the second word. Like the second word, the first word is going to attend to the second word, it's also going to attend to itself, and the third word. So if we scale up this sequence length to 1,000, then the complexity will be like 1,000 squared, because we need to like do this operation
The
for the whole.
transformer, does it still return a sentence? So you put a sentence in, it does the attention or self-attention. Does it do anything else to it?
Yeah.
Because I would think it returns just another sentence, maybe just a different dimensionality or so.
Yeah. So the output of the transformer is, well, it depends on what you want it to be. You can put any layers as output, but this self-attention matrix, which is the one that does the operation, it's like central in the transformer architectures. It's the one that actually does the learning. It's the one that actually boosts the accuracy, and yeah, it's a square matrix with the size of your sequence.
Sure. Right, thanks.
Yeah.
Okay, is that clear? Okay, yeah. So, for example, the length of the sequence is m, right? Then the complexity will be m squared. And again, because this paper is actually heavily emphasized on image, audio, and point clouds, when we use this transformer in images, which means we're kind of unrolling the pixels in an image. If we have an image with resolution of 224, means we're going to have 224 squared, which is like very large for a computation. So we need to like kind of address this problem. And how they going to address this problem? So we can look at the image. So if we see here, in the vanilla transformer, the query key values are coming from the same input, are coming from the inputs. So this is why the example I gave here is going to be like have a complexity of m squared, because everything is come from this sentence, for example. It can be sentence or any unrolled pixels. But here they make it difference that the query comes from a latent array, while the key and values come from the inputs. This way, we can see that instead of having a m squared complexity from the inputs, we can reduce it to m and oh my god, sorry. Sorry for my drawing. Yeah, so because we don't multiply m with m, we now multiply with m and n is much smaller than m, we can reduce the computations. So that's the like very basic idea that they want to do here. Okay.
So the latent dimension would essentially be yet another sentence, but a shorter one.
Yeah, well, actually, something that I'm not really clear in this paper, they mentioned that this latent array is learned, but I don't see how they train this latent array. But I think we can select from this images, basically this part is the one that will produce the output, right?
Yeah.
Because this is the part that produces the logics. Well, every stage, we're going to like kind of fit in the input. I'm not really sure how this latent array is trained once again, but
or initialized. That was also something I was not quite sure. If you start on the left, what do you put in for the first query?
Isn't it a convolutional network? The queries. So the latent array it's a convolutional network, right?
I'm not sure. I don't know if I misread it, but I cannot find it. I read somewhere that it's learned, but I cannot find how they train the initial latent array.
I would have thought the convolutions were somewhere in the cross attention, maybe. You're right. Actually, the queues might be those convolutional representations.
I don't think they mentioned that Q is the CNN, but if anyone recognize something, just feel free to speak up. Yeah. I'm not sure about the, let me see. Oh, I cannot really find it, to be honest.
Yeah, I mean, they just say that they just say that the Q is derived from a learned latent array with index dimensionality n less than m, where n is a hyperparameter. So it's probably just a network that does the mapping from m into n, and then so it's like a dimensionality reduction. So you learn a network and do the mapping. They do say somewhere that they use convolutional networks. I can't remember exactly where, but they use convolutional networks here. So I guess you can learn that mapping however you like.
It's just weird because the transformer acts on it, right? So the transformer changes this representation. So constants throughout the network.
Yeah, so what they're doing is that they're changing the self-attention part of the transformer by this, what they call cross-attention. So because the self-attention takes queries and keys and creates self-attention with that, right? Because queries and keys are both driven from are both taken from the input.
Yeah.
Here instead, they do something, they do a previous step to compute the queries or what goes into the queries. So they reduce the dimension, and then it's not a self-attention matrix anymore, which is, I guess, why they call it cross-attention. But it doesn't scale with the size of the inputs, which is what's really important.
Sure.
Yeah. So yeah, okay, we can continue. Where were I? Okay. Okay, I think we can just look at this. Actually, I think a very clear visualization of the model. So I guess the idea why they come up with such an architecture is that we always like kind of imagine a query in an attention is like a question or information that we want to get from the sentence. Like for example, we have two let's say we have 2 sequence. The first sequence is the input, the second sequence is the output, and for example, it's a machine translation from, for example, French to English. When the model is trying to reconstruct the English sentence, which is the output sentence here, the model kind of like wants to get information from the French sentence. What information do I need to translate this to English? So I can imagine the high level understanding is like that. So in order to that, the English sentence, the output here, I mean the upper part here, kind of like asking query multiple times. And this is why the input, or in our example is the French sentence, for example, kind of attended so many times. So it's like the English sentence like kind of ask, hello input, I have this question, I have this query, I want to know information about this query. Please give me information that going to be useful for me to construct the English sentence. So this one keep asking the query to the French sentence, and then the input will give you the answer of that. And by doing it iteratively, it's like we can't like the first time the query is asked, we might not get a lot of information, and it's going to like repeat it again until we have enough information to produce the output. So I like kind of high level understanding of that. And we can also see that this input is actually going to affect the whole stages. So yeah, we can use what we learned in the past, and I mean in the previous stage, to find the next query for the next stage. So we kind of like come up with useful queries. And because it's also like sharing weights, it looks like recurrent neural networks, right? Like this latent array is the hidden units, and this byte array is just like the input. So I think basically that's the idea of that. And if we also see here, actually we don't fully get rid of self-attention, because inside this latent transformer, we still do the self-attention, because this latent transformer is the same with the vanilla transformer. But now, because we are going to do the operation of attention in this path, which means it's not going to be a very huge matrix like the inputs. It will be only the scale of n squared for the self-attention inside the latent transformer. So again, like this n needs to be also small enough that it doesn't blow up in the self-attention layer inside the latent transformer anyway. So, okay. Yeah, I think that's the actually general idea of how this architecture works and why they come up with such an idea, which I think really makes sense. It resembles the RNA also. Okay, let's see what do they have again here. Oh yeah, they also mentioned here that in these experiments, they use n, the latent array dimensions equal to 1024. And they also have ablation studies in the appendix of the paper that saying that using number larger than this, actually it reduced performance. Probably it will create overfitting.
The input array, the latent array has also another dimension, right? So it's n cross d. Is the d also variable? What constraints are on that? But the d has to be the same as the input array cross-attention dimension, right?
No, because the Q, so Q is also an operation in the diagram. That Q is also an operation which maps the input into the same dimensions as keys and values. So that latent array can actually have different dimensionality than the input array. And I don't know if they actually make it of different dimensions, but there is still something that is not quite. So the latent array actually has less examples than so if we're speaking about an image, the byte array will be all the pixels in the image, and the latent array will be a subset of the pixels, right?
Yeah, something like that. Or in the sentence, it would be a shorter sentence of some maybe higher syntactic features.
Yeah. So that was not. So I understood that part, but it was not very clear to me how they, because they say this is, you just learn the latent array. It's not clear to me how they actually do that reduction. Like how do so n is a hyperparameter, but is it like central to? So how do you pick which pixels or words are going to be used in the transformer as a latent array?
I guess that is learned in the cross-attention, but I would guess that the choice of dimensionality here is also an architectural choice that actually is important to some extent.
But is that differentiable? Like, if you have to choose n pixels or n words, it's not differentiable. So how do you learn which pixels to choose?
In the cross-attention, right? You would learn what maps between m cross c to n cross d, right? That would be a learned transformation, I would guess. That's why I was confused. How do you initialize the array at the very beginning? Do you put in just all zeros and then let the self-attention then impress
Yeah, but
information?
It can't be all zeros, because if it's all zeros, then it has dimension m as well. No?
The latent array?
It can be all zeros with dimension n, but I don't think that's the case here.
The first query would be interesting to see what the first query is actually doing.
Yeah, and okay, I see. Because the latent, okay, so that makes sense. It's just an array of size n by d with learnable weights.
Yeah.
Okay,
the learned weights are in the cross-attention, right?
Yeah, but it's like an embedding, right? Embeddings are a matrix, and you learn the embedding through the iterative procedure, right? So through the gradient descent. Okay, I understand now. I had completely misunderstood that part of the architecture. I thought that the latent array was derived from the byte array, what they call here, but it's just an embedding matrix, or a latent.
Yeah.
Okay.
An embedding sentence, right? Because it has a dimensionality to it as well, which somehow seems to be position dependent.
I have exactly the same question actually for this D. It's like they don't explain it how this is derived, like what is D?
Yeah, D seems to be like a latent dimension, and n is then like a sequence in this latent space.
Mm-hmm. Yeah. Okay.
It's quite crazy, but cool.
Okay. Cool.
Yeah. Thank you. Okay. Well, I think that's all in terms of the architecture. If anyone wants to have any opinion, otherwise we're going to move on to this positional encoding. So it's actually the same thing that is implemented inside the vanilla transformer. So I will say it's not something really interesting in this paper. I mean, we can just like give some refreshment. What is this positional encoding doing? But it's not the key of this paper that actually we have discussed. Yeah, so basically this part is saying that because transformer is a permutation invariant, which means that if we randomly shuffle the sequence, like for example, a sentence, if you randomly shuffle the words within a sentence, basically the output of this attention will be the same because we lost that order of the words. That's why they say it's permutation invariant. And how they address this problem is that by adding positional encodings, which also again implemented in the transformer, in the vanilla transformer, which basically we make use of the concept of Fourier feature positional encodings. So like we have like a different waves with different frequency. Again, I'm sorry of my horrible drawing. We have like waves we have waves with different frequencies, and we kind of like the high level understanding is that, for example, we have a word that is like here, and the next word will be here. Oh my god, it's horrible. The words that are sitting next to each other will have similar numbers in the high frequency waves, but they will have different values in the low frequency waves. So this is kind of a technique that they use in transformer, and they claim it's very what's the word, like it can be extended to different modalities, not only for text. Yeah, I think they mentioned it here, like because yeah, it can be naturally extended to multimodal data. That's why they really like this kind of positional encoding, and it's also learned. So we don't encode it in the beginning. How we going to like see the order? It's just basically learned in the model. All right, so yeah, I think that's all in terms of architecture. Next is about the experiments. Something interesting that actually here they very emphasize on images, audios, videos, and point clouds, but they don't talk about text at all. So I'm like wondering why. Is that because they think that it's going to be more useful in images because that quadratic complexity is like more prominent in image because you need to handle the pixels. Well, in the NLP, we're not going to have like a million words in a sentence. I don't know. So if anyone has a comment on this, the benchmark.
I wasn't quite sure how they go from image to video. In an image, right? They had m to be the number of pixel positions, right? Whereas in a video, you would have time take on that role of a sequential ordering. Right? So the question was then, does the image dimensionality become the latent dimensionality of the input sequence? I'm probably very confused in saying that, but you know, when we had this input, it was m cross c, right? So c for a single image would be probably like the three color values, red, green, and blue. Now, if we map this to a video stream, would then m become the time and c would become very, very large because it's the pixel dimensions?
But you just have to define the length of the, so how many frames? I think they use eight frames at a time. So how many frames you're going to attend to at any one time, and that's your input. So your input becomes of size pixels. So all the pixels in one line, and then.
So your m is essentially becoming 8 times the number of pixels in a.
Yeah. So if your image is 8 by 8, you have a matrix of size 64 by 3 by 8, which would be your frames.
That
That's
would
your
be m.
input.
Yeah, that makes sense. Thanks.
Yeah, here they put an explanation. I think they just unroll this, right, for this time dimension, what they mentioned here. So we get rid of those 4 dimension in the video. Yeah. Okay. Okay, so there's something like I'm not really sure about what they mentioned here with this inception style preprocessing. They mentioned that for the positional encodings for the image, they do inception style preprocessing, which leads to distorted aspect ratio. And they mentioned that in the earlier experiments, they tried using image coordinates instead in order to, I guess, in order to avoid this distorted aspect ratio, but they found that the model overfits. But my question is that if it might lead to distorted aspect ratio, isn't it going to affect the model also? Which I'm not really sure. And then the next part is they talk about the hyperparameters they use. They use a LAMP optimizer that they mentioned because this optimizer is built for transformer-based models. The number of attain is 8 times. It means like the number of how many this input fed into the model. So that was 8. Yep. They also mentioned again in this image net that this model overfits without weight sharing. And then how to address this? They make sharing weights for all of the layers except the first cross attentions and the latent transformer, which resulted in 44 million parameters. Okay. I think we can just look at the results for in this. I'm sorry, where is the table? I thought I saw something. Oh, this one. So this is the results of the experiments for images. The first block here is only using the RGB values without the positional encoding. This one is the one like the first one plus the positional encoding, and this one is the transformer and perceiver. So we can see that ResNet, as we mentioned before, is based on CNN, which has inductive biases. Well, perceiver doesn't have the inductive biases, but then the results of perceiver is on par with ResNet. So they emphasize here that even though we don't have the inductive biases, we can have the similar performance. Hence, our this architecture is more generalized for any other modalities.
I have a question. Isn't the VIT also a transformer?
Yes. Yes,
So
the
why
VIT
are
is also a
they?
transformer.
So why are they not putting them on the same comparison level?
To be honest, I haven't read about this VIT, but I assume they have some inductive biases as well.
Yeah, so the vision transformer, so it uses some of the structure in the image to downscale the size. So
right, yeah.
I can't remember exactly what it is, but that's 16. It refers to,
I
think it's
the grade of
subsampling.
pixels. Yeah.
Yeah, so it uses the structure in the image to reduce the size of the self-attention matrix, which means that it's not attending to the whole image at once. So it has that inductive bias. So you can't use the vision transformer for text, for example. It doesn't work.
Thank you, Carlos.
No worries.
Okay, great. The next table here, which is interesting, that shows how this ArrayNet and vision transformers will suffer when we randomly permutate the pixels. We can see the performance drop very severely, which shows that they heavily rely on the inductive biases of the input. While for perceiver and also transformer, because we get rid of that inductive biases, even though we randomly permutate the pixel, is still perform really well, the same performance, in fact.
There's actually to me, this is a very crazy result because they do like a random permutation of pixels, which means that the image can look like whatever. It can be like a blur, and the perceiver would still have the same accuracy. So it doesn't care about the order of the pixels. It just cares that the pixels are there.
Doesn't it depend on the percentage of swapped pixels? And if the receptive field is much larger, then essentially the noise that is being added is fractionally smaller, and that's maybe why it's just more robust.
So that's it, right? It's attending to it's looking at every pixel in the image, whereas the other methods cannot look at every pixel in the image for whatever reason, like either because they're convolutional networks or because they don't have the computational capacity.
Yeah.
But to me, this is like this is a crazy result. It's like, well, yeah, you can take the image and just move it around. We will still recognize what's in there.
How many percent of the pixels were swapped?
Oh, okay, we need to take a look more. Permuted.
Well, if you think of MNIST and then you swap 2 pixels around, you would still expect to roughly get the number right. So it's maybe not that surprising.
Yeah, but look at the drop in the other architectures, right? Which means that the image has been there you go. Did you find them, Inneke?
No, because they didn't mention about that. I can show you. The permuted this one.
Because that would mean that you would have to change quite a few pixels, right, in order to.
Yeah, no, they randomly permute all pixels on each image independently. So
they don't mention the thresholds of like how much shuffle. But this also leads to the questions, and what is the use of the positional encoding?
Yeah,
but they do say in the second we randomly permute all pixels on each image independently.
they should show pictures of a simple data set and whether it's still humanly possible to figure out it's a dog or not.
This also raised the question, like if it is so good at detecting randomly permutated things, maybe it's more vulnerable to adversarial attacks. You can just put a permutated dog and you will confuse your model.
Precisely.
Isn't then almost looking at the numbers of different hues that it's getting in an image? So, you know, I've got this many of this green, this many of this blue, this many of this red. So it's thrown away all the positional information so that if I get a similar photo with similar coloring, it will just give me a similar classification. So, you know, really you're not using the positional information to detect a tree. You're just detecting, I've got a lot of green in my photo. So then finding similar, so if your classes are very different, if there's only one class that has a lot of green in it, you're fine. If you have different species of trees or something, you might then trip it up. It might depend on the problem that you're applying it to.
Yeah. There's an interesting, so in the explanation that they give an interesting intuition on what is happening, which is that so they also do the fixed permutation where they do the same permutation on every image, and the other architectures are still able to maintain some accuracy, which according to them suggests that ResNet and Vision Transformer can learn that there is a permutation in the data and kind of filter for that. But when you randomly permute the pixels on the image on the images independently, that they're not able to pick up this permutation, whereas the perceiver can. So I mean, it's interesting to think about how these models are learning the structure of the data, right? So if there's a fixed structure in the data, both the ResNets and the Vision Transformers will be able to pick up that structure and be able to produce a good result.
Yeah, nice.
But okay, my question again is that then how is this positional encoding contributing to this perceiver? Because now we kind of we can randomly shuffle it.
Yeah.
Then how much is the impact of this?
Yeah, but when they do the experiments, they train on the permuted ImageNet. So it's not like they test on the permuted ImageNet. So the positional encoding is also learning which.
I see.
So
yeah.
if they should attend to another pixel or not.
Okay, cool. The last part, there are two other experiments about with audio and also point clouds. That for audio, this perceiver outperforms all of any other state-of-the-art methods, especially for audio and video. That is, yeah, it's like very phenomenal in my eyes. For the point clouds, they compare it also with PointNet++, but they're not as good as PointNet because in PointNet there is some extra pre-processing that use some extra geometric features and some augmentations that they don't do here. So they claim perceiver is better than any other like generic models not using augmentations. Okay, cool. Yeah, basically that's all. Oh, one thing about the ablation studies. Oh, I think we missed one part. It's the attention maps. Sorry. They put here also the attention maps of the model. This is the, because there's, as they mentioned, they have a weight sharing. So for the 2 up to the last layer, which is this one, and this is the second layer. Yeah, so we can see that in the first layer, the attention maps can still see the dog. These small boxes represents the channels. And we can see for each box or each channel, we can still see the dogs. If you can see really clearly here. While on the other layer, in the deeper layer, it just look like a tartan-like patterns. So again, we don't know whether this, like how this attention maps are impacted by the number of attempts, or maybe the number of self-attentions inside the latent transformers, right? Because we also have like latent transformer inside this stages that might do the processing, like might do a lot of the work instead of the input attempts. So I don't know if anyone wants to give a comment for this attention map. Yeah. other than that, the last thing that I think a bit interesting is the ablation studies, where they show the hyperparameters impact that increasing the latent dimensions will cause the model to suffer, probably create overfitting. But then for other hyperparameters here, the number of latent dimensions, so yeah, other number of the input attempts, like how many we want to fit in the inputs, and also the number of latent transformers. The greater the number, the better the performance, which also supports the hypothesis that the bigger the transformer, the better the model is. Okay, yeah, that's all. Any other comments?
Can you just go back to that last image that you just showed on the parameters and how they really altered them?
The ablation studies?
Yes.
Yeah, this one.
Yeah, that one. Here they're saying latent dimensions and latents. Is one of these D and the other one N in the size of the latent array?
Mm-hmm. What the sense that I get from this paragraph here, they mention that the axiom in this element was the number of latent dimensions. Optimization seemingly become unstable when using 1024, and then this 1024 is the value of M.
Okay.
Yeah, again, they don't mention D here.
Okay.
Which is something I'm unsure about D. Well.
Okay, thank you.
Yep. Any other comments?
Okay. Just as a clarification point, D is or at least from the notation in section 3, it seems like D is the dimension of the queries. So it is going to be a hyperparameter. Normally it is set as the same dimension of the keys and values. So it is going to be C, because otherwise you can't do the Q times K transpose.
Yeah, I thought about the thing too. Like, I thought, like, mathematically, how can you do the dot product of these two metrics if the C and D are different? But
so yeah, so you can't, because Q, if you go back up, so normally in transformers they say that all these inputs can be of different size, because this Q, K, and V, they do a mapping into the correct dimension. So the output of Q and K is it should match, because you have to do Q times K transpose.
Yeah.
So if they just choose D to be the same dimensions as the output of Q, then that's it, right? You don't really need to do that Q transformation. It actually, I would be surprised if this Q is not just an identity mapping, and then K maps from M times C to M times D. So you can do the, does that make sense? Because the latent array is already learned, and it's already in dimensions N by D. So Q doesn't really need to learn anything. You're already learning the latent array. So why put another learnable weight on top of that?
But wouldn't the generation of Q from N cross D also be something that is learned? I would have thought that N cross D is not constant, right? Because this latent array changes as it propagates the network.
Well, they don't specify this cross-attention layer, right? So maybe it's just taken from the literature. We would have to see what like how the cross-attention layer combines the latent array with Q
Yeah.
And K and V.
And then where the learned parameters actually sit.
Yeah, but what usually happens with, or what has been done with transformers previously is that they show that all these can be different, but then they set them all to the same value.
Yeah, the dimension in which Q and K are what do you call it? Tensor. This is like a sort of scalar product, right? So that dimension is the principal variable over which the contraction happens. And that could be freely chosen, which is neither one of ND, M, or C, right? It could be any other internal one, if I remember correctly.
Yeah.
Okay. Are there any other questions? Comments?
It's a really cool paper. I think it's a very interesting idea.
Yeah, maybe they will open source the code so we can all see what the dimensions are.
Yeah.
Okay. Okay, so thank you everyone for attending. Thank you very much, Inneke, for this paper. It was really interesting, and hopefully we can see more about this architecture in the future. Just as a brief reminder, at nPlan, we're still looking to grow our team. So if you know anyone or you would like to apply yourselves, please go to our careers page. We have plenty of positions in machine learning, data science, software engineering. Please do take a look and apply if you're interested, or tell a friend if your friend might be interested. Otherwise, thank you very much, Inneke, again, and we'll see you next week.
Thank you.
Bye. Thank you.
Cheers. Bye-bye.
Bye. Thank you, everyone.
Bye.
Bye.
Bye.